Welcome everybody to another Origin seminar. Just to let you know, the speaker is fine with having questions throughout the talk, so just raise your hand and I will read it from the chat. Is there anything else?
No, I think I will just pause a little bit.
Ready?
Yeah.
Okay, so you can go ahead and introduce the speaker now.
Okay, yes, we have Agustín Herón here. He's coming from Chile. Last year, he finished his bachelor at Pontif Universidad, Católica. Now he is applying for be a PhD student in different universities, and he has been working with Cristobal Petrovich, who was posted here some years ago, with me, and working on three-body problem, specifically also understand the Lagrange points, and also including embodied and hydrodynamical simulations. So you can make questions during the talk. Okay, thank you to be here.
Thank you for the introduction. Well, my name is Agustín Herón. I'm from Chile, so already know that. Also, I've been working, as one said, we were trying to analyze Lagrange points in the context of the planetary disk using both hydro and embodied simulations. I've been working with my undergrad advisor, Professor Cristobal Petrovich, with Juan, who's also here, his PhD. Postdoc Carolina Chalambos is also part of the team. And lastly, Pablo Benitez Jambay joined us to continue our work. So, as I said, we are going to be talking within the context of the planetary disk. So we're going to be heading at the end of the presentation towards hydro theory. But before getting into that, I need to stay clear with some previous basic concepts. So we will start talking a bit about what the restricted three-body problem is. In particular, we're interested in this because this is when you recover the Lagrange points. So in this formalism, you will have two larger bodies, typically M1 and M2. And you have these two bodies orbiting in the same plane, and eventually you add a third body, a massless particle, which will be called typically from now on as a test particle. So you can, from this, easily write down the equation of motion for this test particle, where we have this mu parameter, which is just a relation between the masses of the two larger bodies. And also here, P1 and P2 are the distances between the third body. What is also important to note here is that we have a system center. The origin of the coordinate system is at the center of mass, and also it is co-rotating. So in this case, we will have the Lagrange point to be static in this coordinate system. And we can, the one who did this the first time, discovered the first collinear points because they are located in the y=0 axis was Leonard Euler back in 1765. And 7 years later, Joseph Louis Lagrange discovered the two remaining ones, the triangular points, which are here in this animation. You can see now, you can see here the collinear points in color blue, L1, L2, L3, the triangular ones in color yellow, orange, sorry, and you see how these are evolving as we increase the relation between the two masses. But now we know that the Lagrange points are there. These are equilibrium locations, so we don't have the velocity, nor the acceleration terms in the equation of motion I showed. So now we need to ask ourselves: are these points stable? The question is, for the first case, in the case of the collinear ones, if we do a simpler stability analysis with perturbation theory, we can find that these are the unstable points. But in the case of L4 and L5, we can derive a relatively easy condition that, taking the case, for instance, of Jupiter, which is a larger body within our solar system, it's largely satisfies, as you can see. So we now know we have the Lagrange points. L4 and L5 are stable ones. What are the typical orbits we found around these points? So in this case, you have here L4 and L5, L3 here. If you put the test particle near whether L4 and L5, you would expect to have these top three orbits, which are kind of close relative to the Lagrange points. And in the case you move the particle farther away from these points, you get what's called a horseshoe orbit. And now apply this to one case near to us, within our solar system, the case of the Jupiter Trojan. So we know we have several observations. We have quantified the number of total Trojans we have, and we observed that there is a symmetry. So getting back to the title of the presentation, we do have symmetry, even if we don't have gas as a fluid species within our protosystem. So in the case of the Jupiter Trojans, you observe a prominent asymmetry here, about double number between one point with respect to the other one. Another interesting feature that I want also to mention you about this interesting restricted three-body problem is what's called the Jacobi constant, which is just another relation you can derive from the equation of motion. You can find this is the velocity of this particle, its potential energy, and this constant called Jacobi constant, which essentially tells you, since we know that the velocity must be a positive quantity, what are the forbidden regions, dynamically forbidden regions for the test particle. So in this figure right here, you're observing how as we change this value for this constant, we get more freedom for the movement of this particle. So taking one step further, an application for this would be the case when you want to put a spaceship in space for the sake of redundancy. You can use this kind of tools to do that analysis. So now we're ready with the Lagrange points. We know that those exist. What are the conditions for stability? We do have stability for the triangular Phonon 5. So what happens when we put gas into the equation, when we put fluids? Well, do we expect to have Lagrange points? Do we, in case we have those, do we expect to find some substructures within those regions? So we know that most of the most common features within protoplanetary disks are rings and gaps. We also know about the existence of spiral patterns, such as spiral density waves excited by protoplanets. But what about Lagrange points? So we know these points are typically located in the co-orbital zone of a protoplanet. So we need to look into gaps if we want to take these Lagrange points. And if we do so, for example, by hydrodynamical simulations, you get this first stage of this, let's call this a time evolution of a typical time evolution of the Lagrange points. We have a typical horseshoe. As I told you before, we know that these are the type of orbits we would expect. So we have this gas here, this ring gap here. Sorry, this gap of gas. And as time goes by, we eventually get the formation of substructures. In particular, we have vortices, in this case in both L4 and L5. And eventually, when the gas completely depletes, we get, or we can recover somehow what would be similar to the case of the Jupiter within our solar system. So now, going back to to protoplanetary disk, we observed this. For instance, this ALMA data showed that we have some asymmetry, what could be potentially Lagrange points. We have here some noticeable difference between those kind of structures. And also, if you run the hydro simulations, you get the same kind of asymmetry. Another interesting case, also one work on it, is the case of the disk HD3296, where you have this crescent shape here, substructure, which could be also potentially understood as a Lagrange point substructure, accumulation of gas and also dust. So how do we deal with this symmetry? So first, check we have done the analysis of the restricted three-body problem, and now we will take a step further and include some other assumptions in order to understand the asymmetry in the n-body case, and eventually we will get to the hydrodynamical form. This is a comparison between what we know, the restricted three-body problem, from now on RTBP, and now what we are going to do is use a theory developed about 20 years ago by Thomas and Carby, where we have a more constrained system. In this case, we will have a massive central object, a star, a zero-eccentricity planet, and a co-orbital test particle. Why are we doing this? Because if you write down the most general form of a Hamiltonian for the test particle, with these assumptions, you can start to make some simplification and eventually recover a final Hamiltonian, which is more useful to make analytical analysis. So what we do first is we know that since we are putting the origin of the coordinate system at the central object, the indirect term is not negligible. Then we will use the assumption of a co-orbital test particle. So we can rewrite the indirect term, this one right here. So that's pretty useful. And finally, we take the Hamiltonian average over the time scale of the radial motion. This is we do this in order to get the analysis only for circular test particles. So this is the final Hamiltonian, as I was telling you, pretty simple. And this is the important part, where we can introduce some asymmetry coefficient that can produces what we want. In the case of, for instance, the Jupiter Trojans. So, this animation. So as you can see here, in the case where we don't have asymmetry, we recover what we know from the previous theory, the restricted three-variable problem. But when we include this asymmetry term, we get to know that two interesting things are starting to happen. The first one is that the location of the Lagrange point are shifting depending on the sign of alpha. We will talk about this in the slides. And also eventually you get to a critical value where you have a merge between L3 and, depending on the sign of alpha, L4 and L5. So that's the critical value. So what's the symmetry coefficient? It's just a dimensionless quantity that allows you to measure the variation of angular momentum that the planet is experiencing. In other words, we have migration. So depending on the sign of alpha, you will get an inward or outward migration. So not only that, but we can also have a distortion of the orbit of a test particle around this planet. We, in this case, are talking about, just to make the connection with the protoplanetary framework, central star and protoplanet. And you see here, I take the case of alpha positive, so the planet is migrating outwards, how you get distortion of the orbit described by the test particle. So now we have the theory. Let's test with numerical simulations. We use rebound and rebound X, in particular rebound X, in order to have this artificial migration, since we know that alpha it's a measurement of migration of the planet. So using the relation that I showed before, you can eventually write down the typical time scale of the migration. In rebound X, since it is an artificial migration, we have an exponential migration. So we need to characterize the time scale of the process. So we have a relation between this time scale, the initial asymmetry coefficient. So this is pretty useful because we can now set a relatively symmetrical configuration and then evolve it and see what would happen depending on what the time scale is. Also, we have the mass of the central object, the mass of the protoplanet, and its initial semi-major axis. Now we're going to use a Sun-Jupiter-like system, and we're going to set the planet initially at 10 astronomical units. With that into account, we can now freely set what we want to be the final symmetry coefficient. So we could have a potential initial value and this n, which is freely set by ourselves. So we could have the same asymmetry that we observe, for instance, in the case of the Trojans of Jupiter. And by doing this, we can also now set the simulation time we need in order to observe that particular difference between the amount of material between one point and the other. And we will try this for 1,000 test particles. So after doing this, what we observe is that we do have this asymmetry. And it's pretty interesting that you see how these Lagrange points are shifting. In this case, it's an outward migration. So we know that the L4 and L3 eventually merge. And you can also see how the particle distribution, which is uniformly set initially, tends towards L5. And on the other hand, you have this more explicit. You have the amount, quantity of particles between L4 and L5, and how it evolves with this asymmetric coefficient. So, any question this far?
So basically, that means that a pattern migrations promote or produce a more prominent asymmetry.
Yes.
So how many particles migrate to L5, and how many of them become unstable and leave the Lagrangian point?
I don't have an answer to that, but I should.
So mass is conserved in the end?
Yes.
So the total mass between L4 and L5 is conserved, or you just have
No,
particles can move
no,
out?
yeah, can move freely. Yeah,
How much, do you know the fraction of mass that you're losing?
should probably be about 70–60%.
How that depends on the alpha parameter?
No, it do not depend on alpha, since what we're doing is set the planet, then you put a ring of these particles. So the ones that are farther away eventually will leave or won't be trapped by the planet. So it's actually depending on what kind of initial condition you set. Like, it's not relevant or it will affect or won't be a relation with alpha.
You also have a question
Okay.
in the chat. Does a positive alpha correspond to inward or outward
I
migration?
mentioned it. Positive alpha, it's an outward migration. So then it's gaining a angular momentum, so moves farther away. So now we are ready to make the transition.
I have a question, sorry.
Oh, okay.
When they go outward, do they get trapped by the system, or, so where do they end up?
These particles?
Yeah.
Yeah, they remain co-orbital in the same case
Okay.
as the Trojans. Sorry for this. Okay, so now we're ready to make the transition to hydrodynamics. So we know what's the effect of migrating planet is. We produce asymmetry between the L4 and L5 points. So we now set a non-migrating planet. So we want to have symmetry and see what the effect of the gas is. So if we could have some asymmetry in this case. So final stage, the methodology, hydrodynamical framework. So in order to quantify the effect of the gas, we need to move to the formalism of hydrodynamics. We need to use both conservation of mass equation and conservation of angular momentum. And the question is, how can we recover the Lagrange points within this formalism? That's pretty easy, actually. You can just simply set the velocity to zero, since we are. You could write down the previous system of equation in a rotating system where the Lagrange points are static. So by setting the velocity to zero, and also by providing an ansatz for the pressure. In this case, we're going to be in the thin approximation, so we will be using vertically integrated quantities. So we will replace the raw density by a sigma density, a surface density. If you do that, you can write down momentum equation as this. So you need to find balance between the pressure and the effective potential that the gas within this zone is experiencing. So by doing this, you can write down a co-orbital Lagrange point equation. If you set, now that in the case you set this term equal to zero, you will recover the n-body theory and the results we have from there. And we need to then try to say, well, how do we compute this psi? We don't know a priori the form that the pressure should have. We can take it from the simulations, but this is kind of the tricky part at this stage. So that's what we're going to do next. Try to run some hydrodynamical simulations in order to determine that psi. So we use the Fargo 3D code to do so. In our setup, we define a 30 Earth mass planet with no accretion processes and orbiting a sun-like star at 1 astronomical unit. With respect to the disk, we set the alpha viscosity prescription. We also set power law for initial quantities such as the pressure, the sound speed, and so on. And lastly, we define a low mass for the disk compared to the planet in order to neglect self-gravity effects and also that migration of the planet. So we have all we want. We don't have we have a non-migrating planet. We have the gas. Let's see what we get. So this is before I get to that, I want to show you what the simulation looks like and what is the material distribution. So as you see, as time goes by, we get some asymmetry, and the parameter in the simulation that's regulating this is the flaring index, the flare of the disk. So depending on what's your initial thermal distribution, you will have asymmetry between one point to the other. So in the case F is set to half, you will have a symmetrical case. But if you vary F, that's the interesting part, you will get asymmetry In one case, you will get L4 more prominent, and in the case of L5 more prominent when you change the F. For instance, if you take F equal to 0.75, you get one case, and when you go symmetrically downwards to 0.25, you get the other point more prominent. So we now have an understanding of what's regulating the symmetry in the case of a hydro simulation. So getting back to offset of the Lagrange points. So we know that in the case where psi is 0, we will have the locations, the typical location for L4 and L5, the triangular positions I showed before. So the pressure what's doing to the location of the Lagrange point is shifting them, producing an offset. So we need to compute that offset from the simulations. And what we observe is that in the case we set these simulations with F equal to 0.5, so we have symmetry within our system. And for instance, we vary parameters such as the gas surface is slope. What would the offset of the Lagrange points be? And we observe that, very interesting, the L3 point, it's not shifted, but the triangular points L4 and L5 are consistently shifted about 30, 40 degrees, 14, 15 degrees. So that means this term is important. We need to compute and try to try to set an answer for this pressure profile. And what we can do is simply just use a sinusoid, looking at the simulations. This is a slice of the pressure at the radius of the planet. And you see that in this plot, this seems to be a nice fit for the pressure. So now we can do this for all the time evolution and see if we have a match between the offsets. Just to remember, look here that despite we have a consistent offset, still we do have some variation. So the error is pretty high. So we need to take a look to be careful with this to make eventual statements about why this offset has this wide range. So what I want to show you here is when we fit these B parameters to our simulations, how these are evolving. So in the case we have a good approximation, all of these parameters would be relatively constant through as the simulation evolves. And what's interesting about these parameters is that B3 here is just a way to show the evolution of the pressure within the gap. Why I'm saying this? Because this B3 parameter could be it's constant. So eventually, when you look at this at the simulation, I don't know if you remember the plot I showed at the beginning of the presentation, we have the depletion of the gas within the pressure. So material is getting depleted. So the pressure, since the proportion of the density, gets lower and lower and lower. That's why you see this shape here, this B3 parameter. And eventually, if we recompute with this theoretical approach, the offset of the Lagrange point, we recover one of our previous results from the simulation data. The offset of the L3 point is consistent. And we could compute again the offset for L4 and L5 and see that although there are some difference, if we take into account the error bars, we are kind of similar. We need to tailor this in order to have a better results and better statements about this offset, but it's a pretty good start. We need to tailor our model for the pressures into Planoid a priori.
So, sorry, in this simulation, you remove the potential of the planet and you just add a pressure profile?
No.
Sinusoid?
We have the potential of the planet and the pressure of the gas. We have all the ingredients. You're not making any assumptions. So lastly, going back to now that we know that there's an offset, we can compute how the Lagrange points are evolving in time, how the surface density of the gas is evolving. And you see clearly here, yes, indeed, we of course can see these simulations in animation that we get some point more prominent than the other. For instance, looking at the right panel or the left one, you see that one point is more prominent than the other. But when you measure it, you can see it more clearly through this. You see in the case where we set F equal to 0.5, this means we have a globally isothermal disk. We have a symmetrical distribution of material. So to summarize things up, with respect to the embodied case, we know what the Lagrange points are, what are the interesting features of the RTB problem, which is also the Jacobi constant. And we know what's the effect of the planet in the Lagrange points. We know that as the planet migrates inward or outwards, we get some degree of asymmetry. In the case of hydrodynamics, we know that the symmetrical distribution of gas is, we found this result in the case of a globally isothermal disk, and that the angular offset of the Lagrange point that we observe in simulations is due to the pressure of the gas in non-migrating systems. So how can we apply these theories to one of these disks I showed at the beginning? In the case of LKSA 15, we could say, well, it could be planet migration or the disk temperature gradient. We know that the infer of the disk, which regulates this gradient, could tell us something about. So we look at the data and we see, oh, well, L4 is more prominent than L5. We know that probably we will have some temperature, some specific temperature. So lastly, this is what we will like to use to try and test all these theories. We have an normal proposal to observe the disk PDS-70, where it has been observed that there is some tentative emission in one of the location of the Lagrange points for one of the planets within the system. So when we get the data, we could eventually try to apply all of these theories and see if eventually we could infer something about the local thermodynamics of the disk or some historical planet migration that could have happened in the past. So that's it.
Any questions either in the room or online?
First of all, you mentioned that these L4, L5 are vortices. So do they like follow the vortex prescription, like the dynamics of the gas and dust inside those clumps?
Yeah, well, I didn't mention it, but the hydrodynamical simulations we were running were without dust, so we don't include the effect of dust. That's like the next step in our analysis. So stay tuned, and eventually I could tell you what about the dynamics or the coupling between dust and
How about
gas.
the gas dynamics itself? The gas dynamics itself.
So same question? Yeah. So you could. Yeah, so as you can see here, you do have the vortex dynamics. So you expect the orbits around these Lagrange points to be approximately close. In this case, since we have viscosity, it's not going to happen. But we expect to have this kind of trajectories around, for the case of the gas, around the Lagrange points for and 5. I don't know if that answers your question.
But these L4 and L5 points, like clumps as a whole, would co-orbit with the planet instead of following like the Keplerian flow as usual vortices do, right?
Can you repeat the question?
So these L4, L5 clumps would co-orbit the planet instead of following the Keplerian flow as usual vortices would do.
I would say that you will have the dynamics due to the protoplanets. So you will expect to have this behavior and not to follow a Keplerian flow. That's what they were asking, right?
Yeah. Okay. And also in that figure, does that mean that these L4, L5 points occur inside the gaps opened by the planet?
Yeah, a co-orbital. Yeah.
So observationally, they would be inside of gaps instead of like.
Yeah.
Okay, I see. Thank you.
You have another question from online. Feng Long asks, for PSD 70, dust trapping is only detected in L5. How can this case, the missing L4 dust, test your models?
Well, I would say it depends on the time scales. So eventually you could have complete depletion at one of the points, and we observe that in simulations. Like that answer.
So you,
What about-
so the L4 used to be there and then disappeared, or?
Yeah,
What about a combination of migration and
yeah,
flaring,
that's an
right?
interesting feature we need to try. Yeah, for sure.
That will speed up or slow down depending on the migration
That's
direction.
something we were discussing with one.
So the sinusoidal profile that you're feeding seems quite a linear response of the system. So what's the mass of the planet is in this case?
This
Yeah,
30 Earth masses.
for a 0.05 aspect ratio,
5%.
5%. So it's super thermal.
Yeah.
Like, so is this consistent with the linearization of the potential as well? Have you checked it out?
Yeah.
It looks like you don't need to go to high order modes to.
Yeah, we're also
To model
running,
the-
we're also
the
running
pressure.
Turing sheet simulations to test this. Yeah. Could discuss that.
Yeah, we could talk
afterwards.
more about
Yeah,
it.
okay, yeah, sure.
Another question online from Jess Speedy. In HD 163296, the dust feature is more like an arc, and in PDS 70, the dust feature is more like a clump. Do you think the arcs could be merging L3, L4, or merging L3, L5, where the clumps are just pure L4, L5 points?
I would say that it seems to be just the points, not merging between L3 into L5 or
That means you won't see the merging points. It won't show as if they are merging.
no. Probably at the beginning of simulation, for instance, you could have you could observe if you put, for instance, tracers. But eventually, I believe that the Lagrange points itself will be more prominent. So that's I guess I think I need to try some simulations in order to test this. But I would definitely say that you have the L4 and L5 points more prominent, and you won't have or observe this effect of the L3 point migrating towards one or the other, depending on the migration.
So even when you do see these different like morphologies, you don't think that's related maybe to them merging or
And
not?
also, we need to try simulations.
Also, we don't know how the other effects can affect the asymmetry, because in that case, you're showing or trying to match the non-migrating planet, which embody create symmetry between Lagrange points, including just the gas component. And we show that the gas component depends on the flaring index, how the asymmetry will be. How about if the dust has their own asymmetry?
Yeah.
And also in HD 16 or PDS 70, we have another planet candidates nearby the locations, how another planet can affect. And one question I have is how the other quantities, for example, as the alpha viscosity, can affect this asymmetry on the gas component.
In the case of viscosity, you just will affect the time evolution of the points.
Because if you increase the alpha viscosity, your gap will be shallower in that case, if you retain the other parameters fixed.
Yeah.
So that could be, I don't know, not so much prominent Lagrange points.
Yes. You have less stable regions, so you don't expect to have the vertices for the same time. We're saying less prominent in the case with lower viscosity environments.
And could be the morphology between HD and PDS 70, because one is a clear arc and the other one is like a point-like emission. Due to the Stokes number, I don't know, I'm thinking that if you have a vortex and you have a pressure band, that species will be more centered due to the drift, and the other one will be around the vortex. Maybe that will be an answer for.
Yeah. Something we need to try.
So the
You
next
know-
step is try.
Yeah, you know that we don't.
Okay.
We haven't tried that simulations yet. Actually,
The next is
Yeah.
try multiple data species
Yeah.
evolution and see the
Good
other
planets.
effects.
Yes.
So how long does it take to run your simulation, and how many are we have a lot of beautiful images from ARMA. Other than those two examples you showed, are there other potentially interesting objects with observations?
I believe these are the two more interesting, but
Yeah.
definitely there are.
So
We'll have to see more.
yeah, it's interesting that when you show the different morphologies that a planet can create, because you show that we have the Trojan, which is the last step, but we don't know what happened in the middle. We have, I don't know, resonances and other stuff. But in the early case, we have horseshoe. So can we observe horseshoes on protoplanetary disk?
Mhm.
Is to say the previous, the
Probably we should.
pre-stage of Lagrange points.
We could observe it, yeah.
You have any candidate?
Not yet.
Jess.
And another question from Jess. Fundamentally, why would clumps at Lagrange points be more observable than the circumplanetary disk?
Because
Yes, in that object, for example, why would we be able to observe dust in a Lagrange point but not also be detecting this?
Well, I don't know servers, so I don't really know how to answer.
Oh,
Just
the
can speak
extinction
up as
level,
well.
the extinction level will presumably be different. So it's, you know, it's something that needs to be investigated, I guess.
I would say that the clamps are more wider than the CPDs. That kind of hint
And-
of what kind of structure.
We don't know
we're
how
observing.
the detectability of Lagrange points depends of the mass of the planets at the moment.
Yeah.
Right.
Caitlin says that she agrees with Leo. There are many uncertainties in CPD formation and detection.
Mhm. Yeah. Agree with Caitlin.
Any other questions or discussion? Not, let's thank our speaker again.
Agustín will be here